So, hello everyone. Uh, this video will teach us how to start using Cadence Virtuoso and run simple simulations. First, we will create a library. For that, we have the library manager. If it is not open, we can call the library manager from Tools Library Manager here. So, we are going to create a library. We go to File, New, Library. We give it a name, and this will be day 2. Press OK. And then a pop-up dialog will appear. We will attach to an existing technology file, technology library. Then we are going to attach to the XH018, which is the technology that we are going to use. So we press OK, and then we are ready. We click on the library, we go to File, New, Cell View, and then we are going to write bias NMOS and leave the other options as they are. So we are going to create a schematic view. We press OK. And then a new schematic view is open. So we are going to start populating this schematic view with the components that we need. So we insert new components by using the key I from India. So there is instance. So we press I, and then in library we are going to go to the primitive library, the one that contains the transistors, primlib, and then we are going to open here and search for we're going to search for the transistor NEL. So it is located here. So this is an NMOS transistor, 1.8 volts low threshold voltage. So typically the one that we will want to use in analog design. Okay, we have selected our component, and then we can place it somewhere in our schematic. Then what we are going to do now is we are going to add the rest of the components. Then we go to the analog lib. The analog lib we are going to select ground. We're going to select DC voltage supply. So we need 2. Okay, and that's all that we need. So we move the ground a little bit down, and then we start connecting with W from the keyboard. So we start connecting. going to connect the bulk also to ground, and then finally the drain. Okay, so now we are going to use variables to control the gate and drain voltages. So for V1, we press it, and then we select Q, and then in this pop-up dialog we select a DC voltage, and then we put a variable name. We can put VGS here, apply, and we do the same thing for VDS. Now we have to select the dimensions of the transistor, and here we have the following options. We can select the width per finger, the length, number of fingers of the transistor, and the multiplier. So we can change the dimensions here. The total width of the device will be calculated by an equation automatically. Now we're not going to put values here. We want to control it externally, these values, so we can use variables. So the width per finger we are going to call WF, and the length we are just going to call L, and the number of fingers we are going to call NF. Press apply, and then we are basically ready to run a simulation. Now we're going to save, check that there were no warning or errors, and then we can start launching the simulation. And for launching the simulation there are several options. We have currently 4 user interface to run the Spectre simulator, but we are going to start with the very simple ones. When you learn the simple ones, you can move very easily to the more complex and let's say modern interfaces that have many options. So we're going to keep it simple today. We are going to call the ADE-L. Okay, so we have a window to configure our simulation, and then the first thing that we will do is to extract the variables that we place, so we can give them values. We click in variables, copy from cell view, and then we have our variables here. So in length, I will put the length of the transistor, and we can just leave it in 180 nanometers. Number of fingers we can put, for instance, 4. VDS, we can leave it in 1 volt. VGS we can put, for instance, 0.4 volts. And the width per finger we can just put the number, let's put 8 micrometer. Okay, so we have given values to the voltage sources and to the size of the transistor. Now we can set up the simulation. We press here, this button will give us the analysis that we can select. So we have a pop-up menu also here. And then first we're going to run a DC operating point. So we're going to run a DC simulation. So we click in DC, and then we are going to click Save DC Operating Point. We click Apply. Okay. And in principle we are settled for running this simulation. Now we can do exactly the same thing by clicking Analysis, Choose. So it will open the same the same dialog that clicking here. So we have basically the same options in the menus. Before running the simulation, I will want to show you something. Here in the simulation menu, we can do several interesting things, and the first one that we're going to do is to go to the netlist and then to create a netlist. Okay, so when we create a netlist, what the tool it is doing, it is checking this schematic and then creating the SPICE or spec netlist that it is actually the list that is going to be used for simulation. So we can see here it's just a text file that includes some simulator setup, include the libraries for the models, that are going to be used during simulation, and then it includes the circuit itself. So we have the transistor M0 that it is here. It is a NEL transistor with a width of WF, length L, and then a bunch of parameters to calculate different variables like capacitances, overlap capacitance, etc. Then we have the power supplies, and then some simulator options, for instance, tolerances that are going to be used, etc. And then we have which kind of simulation we are going to use. Okay, so this is the netlist that will be simulated. So it is good to know, and sometimes we have to check exactly what is going to be simulated. The parameters that I set in the variables are here on the top, and global 0 means ground. Ground, it is 0 volts in a SPICE-like simulator. So we are going to close this. I send it to the simulator. I run the simulation. And then automatically it will open a log. It will tell me what the simulator is doing. It will also start a message here telling you if the simulation was successful or if the simulator found some errors. So when it is done, I will tell you some simulation results here. And then we are ready to check our results. In this case, we have run a DC operating point, and we can check our results directly on the schematic. So to check the results for DC operating point, what we can do is just go to results, annotate. We can annotate DC voltages, and then we have the voltages over all the nodes annotated in white. We have 0 that is ground, 400 millivolts that I put in this voltage power supply, and then 1 volt in the VDS that I set. We can also check the currents and other important information. We go to results, annotate, DC operating points, and then I have other information. For instance, the current that it is being sourced by VDS, but it is power supply. The current that is synced, that is exactly the same, 118.2 micro. The transconductance of this transistor and threshold voltage, VDSAT, and other values. Very good, so we have this information with DC operating point. There is a bunch of very useful information that we can also extract from a DC operating point, and for that one we can check the results browser. So when we click the results browser, it opens another tool that is the Viva, the Virtuoso Visualization Analysis tool. And then we have here in the left different folders. So what we're going to go is we're going to go to DC operating point. We're going to open the DC op info, we open we go down the hierarchies. The transistor was called M0, and then internally it has been instantiated with the model M1. And then we have something very nice. So we have a huge amount of useful information here. For instance, we are interested on the we're interested about knowing what is the transconductance. We can find it here. Value for transconductance. We are interested on the value of the output resistance. We can get it from GDS, that it is the output transconductance. If we are interested on the capacitance, we have all the values of the capacitance that have been calculated by the model here. Okay, so most probably we need to do some processing at some time with these values. I mean, so they can be useful for something, then we can bring them to the calculator. Okay, for that, we can open the calculator directly here. We can also take the calculator from tools. Calculator, and so we can open it from here. So there are a few ways to call these tools. And then we have the calculator tool here. And for the calculator, I have a few options to bring this information. For instance, if I want to bring the capacitance, the gate to source capacitance, I just click it, right click, and then send it to the calculator. And then immediately it will send an equation here, an expression. This expression, it is written in a scripting language that it is part of the Cadence environment, and that we are going to learn, because sometimes it is very, very useful to use these expressions when we are doing scripting. So we are going to learn very, very soon. Okay, but for now, we have this equation here. We can do a few things with that. This calculator works with like a Polish reverse notation. We can put the data on the pipe, and then we can do operations with this pipe, with this stack. So we can do different operations. For instance, yeah, we can do different things, bringing things from the stack. Now we really don't want to do this now. What we want to do, it is to bring this equation to my outputs. So if I have the original equation here, okay, I will put it here in the stack, and then the equation that it is placed on the top of the stack, I can bring it to my outputs here. So here I can configure some outputs that will be updated every time that I press the run button. So I can go to outputs, setup, then it opens another window, and then I can click on get expression, and then I have this exactly the same equation here. Then I can give it a name, capacitor CGS. I can add it, and then it appears here. Okay, so I will apply, okay, and then it just appeared here. Now the next time I send this simulation, the result will appear here at the outputs. Okay, so I don't need to search it again in the browser. Oh, I'm bringing it to the calculator. So I can have this. So this is very, very useful. Okay, so I can run this simulation using this IDE, and I can use a calculator. Now we are going to do something very interesting. We're going to save this setup so we can reuse it later. There are a couple of ways to do that. We're going to use the session save state, and I suggest you to save the state in the cell view. So it is going to create a file inside the library with the same name as the schematic, but for the with the state of the simulation. So I don't need to configure the simulation again. Okay, so I can write some description if you want, but we're not going to do that, so we just save it. And that's it. So if I close it, this one, I see that a new view has been created inside this cell that is called bias and MOS, this spectral state. Now, if I want to bring it again, what I do is I come to launch ADL, and I just bring my setup again in session. Load state, and I bring it from the cell view. So it is state 1, and you can have many states. You just have to change the name for each state, save it with a different name. So, and then we have it back, or a state. And here I can change, for instance, I can change the number of fingers. Instead of 4, we can put 8, and then run the simulation, and then it will create a new netlist, and it will run a new operating point simulation. Okay, so as we expected, we doubled the size of the transistor, and more or less it was double the size of the capacitance, and then back annotated the operating points. Now, if we don't want the back annotated operating points, we can bring this back to annotate, and we put design defaults, and then we have the labels as they were at the beginning. Good. Now what we're going to do is to do exactly that what we have done right now, but scripted. Okay, so we have this setup that we like a lot. What we are going to do is to go to session. We're going to go to save OceanScript, and then we have to give it a name. We can already change the name here to something useful, and normally you want to keep it with exactly the same name as your cell. And then I will change the termination of this file to IL, because this OceanScript in reality it is a skill file. Skill is the name of the language that is used to script in Cadence. So we are going to terminate this file in IL. Then I press OK, and then the new file will be created. So we check that this window pop-ups with the file that has been created. So I can just close it, and then if I check it here, I see that there is a new file that it is called well, where is my file? Bias nmos.el. So I'm going to copy this file to a directory where I will keep all the scripts that I do. I created a directory called the script day 2, and I have already a couple of scripts that I put that I'm going to explain later, and then I move the script that I just created now. So you can do this from the command line, or you can use Midnight Commander or some other tool for doing that. Okay, and then that's it. Now we are going to open this script, and for that I go to the main window in Cadence. I go to Tools, Skill, IDE, and then here I go to File, Open, I go to Scripts, Take 2, and then I take Bias nmos. Then I open my script, and then we're going to study this file. So this file first, it has a header that includes the simulator, the name of the simulator that we're going to use, and the analog simulator in Cadence is called Spectre. So there is a mixing simulator that could also be possible to use. There are actually a few simulators that could have been used for this, but we're going to use the Spectre. The netlist that is going to be simulated is located in this place, and the results of the simulation, the files for the simulation, will be located here. And then we have the models for the simulation. The device models are these ones. These are the paths. Okay. And then we have here the type of simulation that is going to be used. And then we have the variables that we put here, and then some options for the simulation. Sometimes we have many simulations that are going to run at the same time. We put the order in which this has to be done. Temperature, typically room temperature 27 degrees, and then run is the command that will start executing. And then we have an equation here that takes the capacitance, the one that we put in the IDE as the output. It takes it from the results, and then it is just going to plot it. So we're going to run this simulation, and for running the simulation, what we use is we can go here to load. We go to load, and actually we can even use I believe it is Control R. Let's see. Run this one. Okay, we run with the button. Then we see here that some things are happening here. There is a log that appears here with everything that happened. And yeah, the simulation is basically finished, and well, it didn't plot anything because this is not a value that can be plotted. But the value is here, and actually we can call that value, and we can call it from the command line here. So this value, it is 27 femtofarads. It has been stored here. Now, why to use the script? So there are many nice things that we can use with the script, and in particular, if there are things that are very time consuming, we want to use things that are scripted. And one of the things that we can do, for instance, is we can use, instead of this plot, that it is totally useful, we can just comment it. We can comment in skill with the semicolon, and then we can use a printf. And this printf works very similar as it works in other programming languages like C. And the value of CGS equal, and then we can put CGS, and then we are done. So we load it again, and the key for loading is Control L, Control Lima. Then we run it, and then the value became 0, so we are just going to leave it like this, Control F. Okay. So CGS was very small, it was femto. So we are going to multiply this by 15. And then I think we should be fine with this. Okay, yeah. So we have the value of the capacitance here. So we can do mathematics, we can actually use many functions that are specialized for the kind of operations that we need in analog circuit design. So we are going to see that later, that every equation that we have in the calculator we can also use here. Okay, so if I want, for instance, to get other information, I will do something like this. I think uppercase it is not useful here, so I will change to lowercase. We can extract the transconductance also. I just change the name. I can extract the gate drain capacitance, CGD, SGM, CGD, and I can extract the gate bulk capacitance, because basically all the capacitance that are related to the gate. Okay, gate bulk capacitance, and then make this a little bit nicer. This has to be B. And finally, CG, we're missing the transconductance. For the transconductance, maybe we can put it in millisiemens. 3. Let's see if that is enough. And let's take also the output resistance. Okay, so I actually need the output resistance, so what I will do it is just divide GDS, and then we can print it here. Okay, so save it, we send it to simulation. Okay, so and then we have the result here in the log. So very good. So we are very low here. So we are going to let's take it in micro Siemens. Oh, this is a bug here. Let's see GM. Okay, now we are scripting. Then there will be bugs from time to time. Okay, now we are okay. So this is 4.2 millisiemens. Actually, we can leave it in millisiemens here. Okay, so we have basically a bunch of information that we can immediately use for building our small signal models. Now, in my video, I am interested in the FT of the transistor. For the FT of the transistor, I need to divide the transconductance and the total gate capacitance. So the first thing that I need to do is to get rid of these minus that are in front. So what I can do it is to file equations precisely as we will do in MATLAB or in any other programming language, for just Python. We will do like this. We get the magnitudes. We test it. Okay, and then now they are positive. Now I can use an equation for FT of the transistor. So FT of the transistor, it is going to be equal to transconductance divided by CGS plus CGD plus CGB, and all of this has to be divided by 2p, and then this will be 3.1492. Okay. $3.141592. Okay, so then we are settled. We are going to print the FT. And then we can put these ones, for instance, in hertz. FT, send to simulation, and then let's see. I mean, we can do the same thing from the IDE, but very often is much easier to do it with the simulator. Okay. we can probably put this in gigahertz, so we can put we divide it like this, and then we get it in gigahertz. And then we have ft, and then we can naturally we can do other things like intrinsic gain or other kind of calculation that we want. One that it is very useful, it is GM ID over ID, so we can get the ID also. ID current, we get ID current, and then we can calculate the GM over ID is equal to GM divided by ID, and we're going to print a nice line that splits our simulation results. And then we got the value of GMID, and then this is just a figure of merit, so it should be okay to put it like this. GMID, and then we save, Control Lima, Control L, and then we get very much the things that we might need for building our small signal model. So I'm going to put line fit here, also line fit here, and then that's it. We have our we have a very quick way to characterize our transistor in a particular operating point. So that we set like this. Now, very often we don't want to set the variables manually, we want to do it automatically, and what I will recommend it is just to create a file that I call it global, for instance, here, in which I have variables with the size and currents and voltages that I need for a particular transistor, and then we can include this file as part of our simulation. And how do we do that? It is very simple. We can include this file just before the analysis, so I'm going to put this file here. So we go load, and then we have to put the file here, and one of the things is that I have to put the path for where it is located, starting from my directory that I opened Cadence. So it will be here. Slash and the name of the file. It is global.el. So all the simulations start in this directory in field 3601, so I have to put the complete path from there. And then now I can just use these variables here that I define here. So I come here, and instead of a number I can put a variable here, L1, NF1, BDS1. We don't have BGS here, So we are going to keep it 0.4 right now. But we have WF1. So we can save. Then we can just send to simulate, and then we have a different setup here, different results. So we're going to change this. For instance, we're going to change the length of this transistor to 1.2 micrometers, and then I will run the simulation. And then we have totally different results, different capacitance, etc., etc. Okay. Okay, so this was the basic simulation and the setup of a script. So there are many other things that we can do here that we're going to discuss later.